In our studies of quantum mechanics, one of the first systems we talked about was the quantum mechanics of spin as investigated by Stern-Gerlach experiments. As you might recall, the idea of a Stern-Gerlach experiment is that you send a beam of particles through a region where you've set up a magnetic field along some axis that's inhomogeneous so that it separates out particles into separate beams based on what their z component of spin is, based on the magnetic moment, which is proportional to their angular momentum, which is their spin. So the idea is that when we had electrons, when we first studied these experiments, we send an electron beam in, and since electrons are spin-1/2 particles, their z component of spin can be either plus h bar over 2 or minus h bar over 2. They split into two beams, and they separate out. They do their thing. In our class, we've been talking recently about spin-1 particles. And we can do the same experiment for a spin-1 particle, which could be like a Z boson, or more likely we have some atomic state that is an overall total angular momentum 1. And we can use that spin-1 particle and use Stern-Gerlach experiments to measure their spin state. Now, as we've learned, for spin-1, there are three possible angular momentum states along the Z axis, or along any given axis, plus h bar, 0, and minus h bar. And a Stern-Gerlach experiment will consequently split a single particle beam into three beams. In this particular case, I'm starting out with a Stern-Gerlach experiment oriented along the z-axis. I send my particle beam in, whatever it is, spin-1 particles, splits into three states, and I'm going to select out, I'm going to block the two beams, I'm going to select out just the beam that has z component of spin plus h bar. Just choosing that beam, and we're going to see what happens as we go through. Now, this is just one particular experiment, but the goal of this is going to be to understand how these Stern-Gerlach experiments work, how quantum superpositions work for different types of particles, for this new spin-1 case, where things are a little bit more rich and interesting than the spin-1/2 particle case. So in particular, we're sending this beam of SZ equals plus h bar particles into a y-directed Stern-Gerlach apparatus. So it's measuring the spin along the y-axis instead. And again, it's going to split it into three beams. SY equals plus h bar, 0, and minus h bar. This one is set up, and our book talked about how to do this, it's set up a little differently so that the beams will spread out, and then the magnetic fields are reversed, so it comes back together and recombines into a single beam coming out the other side. This seems like a pointless thing to do, but what it means is we can go in and muck with individual beams in the middle, like a block 1 beam or block 2 beams or something, and see what comes out the other side, and it will all come out into a single recombined beam in the end that we then feed into another Stern-Gerlach Z apparatus, and we ask what comes out each one of these three things. Now, of course, if I left this out, if I just let this beam go straight through empty space, we know that if we've measured it to be the Z component of angular momentum to be plus h bar, and there's nothing here in the middle, we would obviously measure it to be plus h bar again, assuming that there's no stray fields that are going to make the state change. We're going to be in the same state. So we measure the same thing twice in a row, and we would get the same thing. We'd get all plus h bar, nothing in the other two beams. So that's our starting point. That's what we want to understand, and we're going to talk about this for blocking several different choices of blocking different beams in the middle to see what happens. Now, some reference information. I've written down here the representations of the y basis, the spin states in the y basis represented in the z basis. So that is, if I go through and do the 1,1z ket bra, meeting up with a 1,1y ket, that gives me 1/2. 1,0z with 1,1y gives me I squared root of 2 over 2. 1 minus 1z with 1,1y gives me minus 1/2. Those are those individual amplitudes, and that tells us how to represent this in the z basis. That turns out to be a really useful tool for what we're going to do here, just to know what those coefficients are. The same true for the 1, 0 and the 1 minus 1y states. Notation thing, just so you know, when I'm putting a y subscript on a ket, that means that that is in the y basis. If I'm leaving off the subscript, as I have for these three bras, our default basis is the z basis. That's the conventional choice for basis. All right, what's our strategy to figure out these probabilities? Our strategy is going to be whatever paths we're allowing in the middle here. If we know our initial state, which is the plus z state, the plus h bar state rather, and we know our final state, let's just say the plus h bar state over here. If we know those two states, then to find the likelihood of that happening, we have to find each path that would get us from the initial state to the final state, and find the amplitude, the total amplitude, we'll say how to do that in a minute, along that path. All those amplitudes, don't take probabilities, don't square it yet. Then, once we've done that for every path, we sum the amplitudes for all the paths. That's our overall amplitude for that initial to final process, and that's what we square to find a probability. Okay, let's do that. Let's start out simple. Let's start by saying I'm going to block 2 of the 3 paths in here. I'm going to block the 0 path, and I'm going to block the minus h bar path. So the only path that goes through from our initial state here, the plus h bar z state, to the final states, to the final apparatus, is the sy equals plus h bar state. That's our only path. And I can ask what will be the amplitude to get to each one of these 3 beams. So let's talk about how to do that. What I do, if I want to know, if I want to consider the sz equals plus h bar outcome, what I do, I start with my initial state vector. My initial state vector is the 1, 1, z. I could put a z subscript, but I'm not going to. 1, 1 state vector. That's my initial vector. And then I follow my path. I say, okay, it's going to get over there. The path that works is this top path. In the top path, I was along the sy equals plus h bar state. So we know in our notation, in Dirac notation, the way you ask a question, hey, Mr. sz equals plus h bar particle, are you sy equals plus h bar, is by acting with the bra for that state. I'll act with the 1, 1, y bra. That asks, this is asking, are you sy equals plus h bar? That's what that bra does. And so that bracket there is going to tell me the amplitude, not the probability, but sort of the square root of the probability, the amplitude for being in that sy equals plus h bar state. Next, I say, well, okay, that means I'm in that beam. I'm in that state right now. So that means I am in the state 1, 1, y. So this is telling me, yep, I am sy equals plus h bar. That's what that ket is telling me. So this is my amplitude, and I multiply it by the ket. Technically speaking, this thing here, this 1, 1y ket times 1, 1y bra, that's a projection operator into the sy equals plus h bar state. If you want to think of that as a projection operator, cool. And then I come through here, and now I'm going to ask the question. I want to know if I'm coming out in the s equals plus h bar outcome. I ask another question. I say, hey, this says, are you sz equals plus h bar? That's what that bra does. And again, it's acting on the most recent ket. Any particle in this top beam is in the 1, 1y state. So we ask the question, are you in the 1, 1z state? And that's what we come up with. And when I do that, I guess I may as well just write this out. When I do that, I find that first bracket, 1, 1z with 1, 1y, I actually have that right here. It's 1/2. And I multiply that by the second bracket, 1, 1y with 1, 1z. That's just the complex conjugate of this. That's the other way, so it's just 1/2. And that's 1/4. So I come up with a 1/4 as my outcome in that top beam. Fine. Okay. I can do the same thing to say, what about my sz equals 0 outcome? And here we're going to have very much the same idea coming along. We're going to have, for my sz equals 0 outcome, we're going to say we're starting in the same initial ket, 1, 1 in the z basis, and we have only the same one beam up here. So we ask, are you in the 1, 1y state? And we say, yes, I'm in the 1, 1y state. And then we ask, are you in the 1, 0 outcome? That's the S equals 0 that corresponds there. It's the same calculation, but just different stuff. Oh, I should have put this down here, shouldn't I? This equals 1/2 times 1/2 equals 1/4, just so I don't spread too far over there, so I can use that board space later. I'll put this here. This is going to be, I'm going to put it underneath just to do this. This is going to be, this 1, 0 with 1, 1y is right here. Wait, no, hang on. Yeah, 1, 0 with 1, 1y is right here. That's I square root of 2 over 2 is that first term, times, this term is the same as it was before. So this is I square root of 2 over 4 is my amplitude for that particular path. And then I can do the same thing for my SZ equals minus H bar outcome. And you can already see how this is going to go. I'm going to have, I start my state 1, 1 again. I ask, are you in the top beam in the middle? 1, 1y. I say, yep, I am 1, 1y, all right. And then I'm going to ask, okay, but now are you 1 minus 1, z? And when I multiply this out, the 1 minus 1 with 1, 1 is minus 1/2 times, again, the same final term, the 1/2 there, is 1/4. And those are my 4 amplitudes. So if you want to know, those are just the amplitudes. If you want to know what the intensity is of each of these 3 beams coming out, if you want to say, well, which beam is brightest, how does it look? What I need to do is take the absolute square of each one. So the SZ equals plus H bar intensity is given by the absolute square of the amplitude. The absolute square of 1/4 is 1/16. 1/16 of the particles that were in our initial beam, our initial plus Z beam or plus H bar beam, 1/16 of those come out in this top beam. The SZ equals 0 intensity was, what is this? This is I square root of 2 over 4 squared. That's 2/16. And SZ equals minus H bar intensity. When I do that, that again is the absolute square of minus 1/4. And that's 1/16 again. So what I get is 1 to 2 to 1. The middle beam is brightest, twice as bright as the outer two. And otherwise, this adds up to just 4/16. What happened to the other 12/16, the other 3/4 of the beam? Well, remember, I blocked the middle and bottom paths. Of course, most of this is getting blocked. So I can say that and 3/4 of the initial were blocked. So for this case, 3/4 of the initial things wound up being blocked by blocking those two. 1/4 made it through, and they split up 1 to 2 to 1 in those 3 beams. That's our conclusion from doing this Stern-Gerlach experiment. Okay, that's a perfectly reasonable thing to do. That we've done that calculation. Let me now look, and maybe I should make a note of this somewhere. I want to make a note of these 3 amplitudes. So let me note that down by saying that for the SY equals plus H bar path, the amplitudes for the final SZ were, for this path, those amplitudes were SZ equals plus H bar. Our amplitude was 1/4. SZ equals 0. Our amplitude was I square root of 2 over 4. And SZ equals minus H bar. Our amplitude, I left out the minus sign here, didn't I? Was minus 1/4. We got those results. That's what we came up with for those paths. So this was just taking this one equals plus H bar path, getting those 3 things. All right, let me change the story now. Let me say, what if I change this? what if I block the top path and the bottom path, but now I allow the middle beam to get through, the SY equals 0 beam? It's the same sort of calculation. What's going to change here? Let me erase my my numbers. Maybe I didn't need the board space, huh? Okay. Let me erase my numbers here and see what I come up with. For this one, same sort of outcomes. The difference now is I'm still in the same initial state. 1, 1 was my initial z state, plus h bar state. But now I'm asking, are you in the middle path? Are you sz, sy equals, and let me just change this, are you sy equals 0? I know I'm not rewriting. Are you sy equals 0? So that means I need to make this the 1, 0 y state. And then that means once I've got that amplitude, if I'm in that beam, the 0 beam, that means yep, I am sy equals 0. So I'm in the 1, 0 state. Again, this is a projection operator. If you want to think of it this way, this ket times bra is the 1, 0 y projection operator. And now I ask, hey, are you sz equals plus h bar again? I can do that same calculation. And now I look at this and I say, okay, well, the 1, 1 with 1, 0, 1, 1 z with 1, 0 y is 1 over square root of 2. And 1, 0 y with 1, 1, that's just the complex conjugate of the same thing, I guess. So that's also 1 over square root of 2. So that's 1/2 is the number I would have gotten there. So maybe I should have labeled that. So I've got that. I can do the same things down below, right? I get this case. I'm still, my projection operator has changed from the top beam to the middle beam, the sy equals 0 projection operator. And that means I'll be changing these pieces. What do I get for this one? My 1, 0 z with 1, 0 y is 0 times, and then 1, 0 y with 1, 1 z is the 1 over square root of 2. The 1 over square root of 2 is going to be the same as the second component for each one of them. But this is just 0 because there's no amplitude to measure a 1, 0 y to measure the 1, 0 y state as being 1, 0 z. It just doesn't line up. So we get 0 outcome for that. And then this, we can sort of guess what it's going to be, but let's do the same fix. 1, 0 y and 1, 0 y, changing to the new state again. And again, that's that same one. Yeah. It's gonna, here we've got the same deal where we have to look at 1 minus 1 with 1, 0 y is 1 over square root of 2. And 1, 0 y, or 1 minus 1 and 1, 1 times 1 over square root of 2 gives me actually 1/2, a positive 1/2 for that amplitude. Okay, so I've got that. And what that means is, for this one, I guess I could label these outputs as being the top only outcomes. If I now say, what's my middle only outcome, my middle beam only for SY, I can say that the SZ equals plus H bar intensity is going to be the absolute square of this output, of this outcome. It's going to be the absolute square of 1/2, which is 1/4. The SZ equals 0 intensity, TY, I can really write intensity honestly, that's 0 squared, which is just 0, and the SZ equals minus H bar intensity is that 1/2 again, squared, which is 1/4. So okay, what do I have now? I have a fourth, 0, a fourth, so I've got equal brightness spots on the top and bottom beams coming out, and nothing in the middle for this. If I have taken my SGZ, sent it through as this, and only kept the SY equals 0 beam, I get an even split of plus and minus Z and no 0 Z. That's kind of cool. This only adds up to half the probability, but this says that I also have half of the initial intensity was blocked. So you can already see how this adds up. A quarter of the initial intensity wound up in that top beam, a half in this middle beam, and I guess a quarter must have ended up in the bottom beam as well for the SY states. Each time it adds up pretty nicely to give us our results. Now here's where it gets interesting. Now let me summarize this. For our SY equals 0 path, the amplitudes for the final SZ, let me just copy those amplitudes down again. I had SZ equals plus H bar, my amplitude was 1/2. SZ equals 0, my amplitude was 0. And SZ equals minus H bar, my amplitude was 1/2, all that way. Okay, so I've got those results. Now here's where it gets interesting. Let me now do a third experiment with the Stern-Gerlach device. Let me unblock the top path again. This time, I now have the top path and the middle path both getting through. Remember, they're being recombined into a single beam. So now this time when I add this all together, if I do the top plus middle, if I want to find intensities, what I need to do, remember my strategy, I find the amplitude for each possible path to get from the same initial state to the same final state. I look at those amplitudes, I add them up, and only then do I take the absolute square to find the probability. So in our particular case, I can say that the SZ equals plus H bar intensity. What's that going to be? Well, it's the absolute square of something. It's my first amplitude, which was 1/4, plus my second amplitude, which is 1/2. The absolute square of 1/4 plus 1/2 is the absolute square of 3/4, which is 9/16. Suddenly we have a very strong signal, 9/16 coming out. That's more than half the initial intensity in that top beam. Next, I can say, what is my SZ equals 0 intensity? And there, my first state gave me an I squared root of 2/4 plus 0 for the second one, absolute square. That's just what it was in the first case, right? It's going to be 2/16. That works, okay, 2/16. And finally, for SZ equals minus H bar, that intensity, or that probability if you want to think about it as individual particles, that one is going to be, what do we have here? Well, I had minus 1/4 was my first amplitude, plus 1/2 for my second one. That's 1/4 squared. That's 1/16. So now look at these ratios. At this point, I've got 9 to 2 to 1. It's very bright coming out this, much less here, and even less here. That's how this comes out. 9 to 2 to 1. When 9, 10, 11, 12/16 came through, we should say then that and 1/4 of the initial intensity was blocked. And this is the interesting part. This is where it's actually kind of fun to see the quantum mechanics happening. Because, again, we have a quarter plus a half plus a quarter, we said, for those three paths, was the intensity on each one of those three paths. And we've got it. 3/4 of the total intensity came through. Only 1/4 is blocked now. But it's not just the sums of the probabilities. It's not just 1/4 plus 1/16. That's 5/16, 2/16, 5/16. It's not. We've got a real enhancement of the plus H bar case and a real squeezing out of the minus H bar case. We're much closer to being our original beam. We've gotten much closer to that. And why is that? It's because these amplitudes can be positive or negative. In the plus H bar case, the 1/2 and the 1/4 added. They reinforced each other. So we got that reinforcing of that part. In this case, the minus 1/4 and the plus 1/2 canceled each other out partway. And that cancellation, once you square it, is a big deal. So that's what's happened in this, that we are getting quantum interference between the different paths. And in my mind, it actually makes a lot of sense that as we keep more and more of the information about the initial state by blocking less of it, it makes sense that we're coming closer and closer to getting our initial result back. If this weren't here at all, we expect it to come out just plus h bar again. Well, we're coming out mostly plus h bar when we've let 2 out of the 3 paths through. I think that's pretty cool that it works that way. So maybe this is the point where we can do one more quick little calculation. I won't belabor it much, but just do that last step to say what would happen if I took the bottom path and let the bottom path come back through again. If I didn't block anything at all, what's going to happen? You know in your heart what's going to happen, right? It should recombine into as if this weren't here. But let's see how it happens. Let's look at this. Imagine then that in my plus h bar outcome, I start with the 1, 1 z state, my 1, 1 ket, and I say, are you in the bottom path? Are you 1, minus 1? And the answer is, sure, yes, I'm 1, minus 1 now. And then we say, okay, but are you 1, 1 z? And we'll do that calculation. What's that come out to? Try this again. 1, 1 z with 1 minus 1 here is 1/2 times, this is just the complex conjugate of that. So 1/2 is 1/4 for this. And s equals 0, same thing, got to make this minus 1 and this minus 1. Again, we've got this projection operator, right? My sy equals minus 1 minus h bar projection operator in the middle. And what's that give me in the middle here as my outcome? The 1, 0, 1, 0 with 1 minus 1 gives me minus I over square root of 2 times my 1 minus 1 with 1, 1, 1 minus 1y with 1, 1, that's my 1/2. So this is minus I square root of 2 over 4, if we want to do it that way. Minus I square root of 2 over 4. And then this one, same deal. We're going to say I start in the 1, 1 z, the 1, 1 z state. I ask, are you in the 1 minus 1 y state? I say, yes, I am in the 1 minus 1 y state. Are you in the 1 minus 1 z state now? And for this one, what do I have? 1, 1 with 1 minus 1 is the minus 1/2. Get this right? I get minus 1/2 times 1 minus 1 with 1, 1. That's up here times 1/2 is minus 1/4. Again, I've got these amplitudes, and if you squared them, remember, this is going to look just like the top path. We're going to get 1/16, 2/16, 1/16 if we do absolute squares, just like we had up here. It would be the same intensity profile as the top beam would have been. But adding it all together, what happens for our totals? Where can I put my totals? Let me put my totals here, now that I've used this all up. If I do all 3 beams, I'll find that my SZ equals plus H bar intensity is going to be the absolute square of, let's add up the amplitudes, 1/4 plus 1/2 plus 1/4 over here squared. That's just 1. All right, already this looks promising. SZ equals 0 intensity. Again, we add up the 3 amplitudes for the 3 paths because there are 3 paths to get there. We add their amplitudes before squaring. What's that give me? My first path gave me an I square root of 2 over 4 plus 0 my second path, and this one gave me a minus I square root of 2 over 4 squared. That's just 0 because those canceled out. Yay! And then SZ equals minus H bar intensity. You're seeing where this is going already. I know, but I may as well write it down. I have to play this out to the bitter end. I'm going to add them up. Minus 1/4 plus 1/2 minus 1/4 squared is 0. And so when all 3 beams are allowed to propagate through the middle, and we don't do anything messy with them, when they're all recombined together, we find that all of our signal comes out the top beam, and the other 2, now the quantum amplitudes have canceled out because we add them before we do the square. They canceled out, giving us a pure H bar plus H bar beam. And that actually, for me, is a really fun thing to see happen, seeing that come together. when we put all of the information back together about our initial state, it's still our initial state. Only when we've blocked and thrown away some of that information do we get the full scrambling or partial scrambling of states that split it up into this different thing. And for me, that's sort of the miracle of quantum mechanics, that we can get this cancellation, and it works out so elegantly. I mean, it has to, but it's also miraculous to see those numbers work out to exactly add up to 0 for these two, to exactly add up to 1 up there. It's fun. I like it. So that's my story about doing Stern-Gerlach experiments for spin-1 particles with z and then y basis. I think it's a good way of looking at this, and I hope you find something from it.